Hello, dear viewers. You are on the CrossMoto channel. In this episode, we will step away from the motorcycle topic a bit and touch on something very interesting: atomic energy. In the 20th century, humans managed to harness the energy released during the radioactive decay of heavy elements. These reactions are a source of enormous energy, orders of magnitude greater than what is released when burning a comparable amount of fuel. And only synthesis and annihilation reactions can surpass them in terms of energy release. And this power, humans have mastered both for destructive purposes and for creative ones. The atomic bomb, the Manhattan Project, Hiroshima, all these are stories about the creation and use of weapons of incredible power. Many documentaries and online materials cover this topic, but our focus is on the peaceful use of atomic energy. The vast majority of people know that nuclear reactors are used in the energy sector, as well as a source of power for certain types of transportation, particularly ships and submarines. However, during the golden age of the atom, the 1950s and 1960s, it seemed to humanity that this technology would be used everywhere, from medicine and industry to a compact so-called eternal energy source for private homes and even power units for passenger cars. The military was the primary driving force behind promoting nuclear technologies. They desired everything from reactors and tanks to bombers with flight ranges, only limited by crew endurance. However, civilians also did not want to fall behind in mastering the new technology. History knows only a small number of concepts, and not just concepts, but actual vehicles powered by the energy of nuclear reactions. And I invite you to hear a few words about atomic cars. Make yourself comfortable, enjoy watching. The appearance of the atomic bomb, and a little later the use of atomic energy for peaceful purposes, was preceded by decades of theoretical and experimental work by many scientists. The first atomic bomb was created in the United States in 1945. The United States of America was the sole country in human history that used atomic weapons in Hiroshima and Nagasaki. In 1949, the Soviet Union became the second country to acquire an atomic bomb. In that same year, another important event took place in the Union. The government, having listened to the arguments of scientists such as Petr Kapitsa, Sergei Vavilov, and Igor Kurchatov, made the decision to build the first civilian atomic facility in the Union and in the world, namely a nuclear power plant. In October 1954, the Obninsk nuclear power plant was launched and connected to the Mosenergo grid. The first brick in the foundation of the peaceful use of the atom was laid. The first moving object to use nuclear energy was a submarine. This was the United States ship Nautilus, which was laid down at the shipyard in Groton on June 14, 1952, and was launched on January 21, 1954. The next stage of the nuclear race was won by the Soviet Union. The first surface vessel, and also a civilian one, with a nuclear power plant was the icebreaker Lenin. It was laid down at the shipyard in 1956 and put into operation in 1959. And now imagine how, at that time, people dreamed and pinned their hopes on the new technology, on the new source of energy. In addition to the above-mentioned realized designs and constructions, there was a whole array of prototypes, concepts, and ideas. They ranged from quite logical and well thought out to downright absurd. We can distinguish two surges of interest in ground-based nuclear transport. The first occurred in the 1950s and 1960s of the last century, and was connected both with the arms race between the Soviet Union and the United States of America, and with the firm conviction of scientists that the atom would be fully harnessed in the coming years. The second surge occurred in the early 2010s and continues to this day. This period has a different basis: the emergence of new technologies and materials, the daily expectation of a successful controlled thermonuclear fusion reaction, and a renewed surge in the popularity of space flights. All these events once again motivated a number of engineers to return to refining the concept of the atomic car. Let's go back to the 1950s. Before the idea of designing a car with a reactor appeared, work was already underway on the concept of an atomic tank. The model of the television Odin tank was shown at a conference dedicated to the prospects for the development of armored vehicles, which was held in Detroit in June 1954. The tank was supposed to be a 70-ton combat vehicle, armed with a 105mm T-140 cannon and protected by 350mm frontal armor. Engineers calculated that the reactor, powering the tank's turbine using superheated atmospheric air, could operate at maximum capacity for 500 hours. The second tank presented at the same conference was the R-32. This concept implied the creation of a lighter tank compared to the television. 1. The R-32 was planned to be equipped with a nuclear reactor, which would provide the tank with a range of 6,500 kilometers. The R-32 was supposed to weigh about 50 tons, have 120 millimeters of frontal armor, and as its main weapon, a 90mm smoothbore DC-208 cannon. However, both projects were not recommended for further development. A reactor with an open cooling circuit would relentlessly contaminate the atmospheric air. Engineers calculated that the tank crew would be exposed to serious radiation in addition to external contamination. If the television Odin and R-Tritsat DVA had been built, they would have been far more dangerous to their own troops than to the enemy's forces. The main problem with the concept of a tank with a nuclear engine was that a large range did not mean greater autonomy for the vehicle. The limiting factors were the supply of ammunition, lubricants, and the lifespan of the tracks. In addition, damage to the tank would very likely lead to radioactive contamination of the area. The third tank design was quite unusual in appearance, Television 8. Its weight was 25 tons, and its power plant was a V8 from Chevrolet. However, engineers also considered the possibility of incorporating either a gas turbine power unit or a nuclear reactor into this design. This prototype was also abandoned due to the lack of any advantages over conventional light tanks. By the way, around the same years, experiments were being conducted in the Union of Soviet Socialist Republics and the United States of America to install atomic power plants on board bombers. In America, it was the Convair X6, and in the Union, it was the Tupolev Tu-119. The goal was to significantly increase the range and autonomy of the aircraft. However, here, the engineers encountered the problems mentioned a couple of paragraphs earlier, and the development of ballistic missiles, whose design was simpler and cheaper than a nuclear-powered aircraft, put an end to further experiments by aviators with atomic energy. We need this information to better understand the context of what was happening in those years. Scientists and engineers were working through these concepts, which meant that the body of knowledge in the field of nuclear reactors, their capabilities, and their problems was steadily growing. And the attempt to create a civilian car powered by nuclear energy, or at least to work out the concept, was only a matter of time. Many internet sources, in all seriousness, claim that the Ford Nucleon was the first concept of a nuclear-powered car and almost the only one, but that's not true. In the late 1950s, various design bureaus worldwide simultaneously became captivated by the concept of a nuclear-powered vehicle. The presentations of these concepts took place, roughly speaking, within about a year, and the Nucleon from Ford was just one of them. And since we've mentioned Ford, let's start with it. The Ford Nucleon was presented to the public in 1958. It was a concept, and its model was built in a reduced scale. Ford engineers wanted to use technologies tested on the United States ship Nautilus submarine. The nuclear reactor was supposed to power 2 turbines with steam. It's simple. The car has a certain supply of water which is evaporated by the heat generated from the reactor and turns the turbines. One of the turbines would drive the wheels, while the second, less productive one would rotate an electric generator to power the onboard electrical system. Interestingly, Ford engineers designed the power unit as a modular block system. It was planned to offer several options for reactor modules, for example, ones with increased power or, on the contrary, more economical ones with a greater range on a single refueling, so to speak. It was calculated that the reactor should provide a range of 8,000 kilometers. While not a perpetual motion machine, it is still a worthy competitor to fuel-hungry internal combustion engines. A bit of historical background. American cars of that time were famous for their fuel consumption, and in some circles, fuel consumption was even a point of pride. Your Chevy guzzles 7.9 gallons per 100 week. My Ford gulps Ica. The Ford Nucleon was planned to be refueled as follows. At a service station, the reactor with spent fuel would be replaced with a fresh one, and the old reactor would be sent to a plant for refueling and maintenance. Another question arises. What about radiation safety? Ford engineers were working in this direction. First of all, the driver and passenger were placed as far as possible from the radioactive source, actually in front of the car's front axle. There were also provisions for installing lead shielding around the reactor. The appearance of the concept emphasized the futurism of the entire idea. By the way, at least 2 versions of the car's exterior were being developed, one with tail fins and one without. As you might have guessed, Nucleon remained just a concept. At that time, it turned out to be impossible to miniaturize a submarine reactor enough to fit it into a car chassis. Add to that the weight of the lead radiation shielding. The original S2W reactor on the submarine weighed 35 tons, and together with its protective structure, it boasted a diameter of about 5 meters. Add to all that the not unfounded fear of a nuclear holocaust. Humanity had already learned from the example of Hiroshima and Nagasaki what severe consequences radiation can lead to. And just a few months before the Ford Nucleon concept was unveiled on October 10, 1957, there was an accident with a major release of radioactive substances at one of the 2 reactors of the Sellafield nuclear complex in the northwest of England. Anyone who watched Sarin's documentary is familiar with this name. The original model of the Ford Nucleon is currently kept at the Henry Ford Museum. Another car whose design was intended to use atomic energy was the French Arbel Symétric in 1958. The first Arbel was designed and built by André Loubier with the support of his brother Maurice back in 1951, and it was conceived as a hybrid. An inline 4-cylinder engine from Simca drove a generator, which supplied power to an electric motor. The car was named Symétric because of its symmetry. It's simple. Over 2 years, several cars were produced for experiments and presentations, but the project reached a dead end. Loubier returned to the idea of his own car 4 years later. The second version was developed between 1957 and 1958. It was presented at the Geneva Motor Show in March 1958. For this concept, alternative power units were considered. The first one was a gas generator, but we are interested in the second one. The French wanted to incorporate a 40-kilowatt nuclear thermal generator into the design, which would use nuclear waste cartridges as fuel. The main difference between this unit and the idea from the Ford company was that the French decided to use a nuclear battery instead of a reactor. Like a nuclear reactor, it generates heat, which can be used to heat a coolant and then further transform the energy into mechanical or electrical power. But in such a battery, unlike a reactor, there is no chain reaction. By the way, this technology dates back to as early as 1913. It was then that Henry Moseley first demonstrated an electric current generated by the radiation of charged particles. In general, such a battery was supposed to power the electric motors that would drive Arbel Symétric. Radiation shielding was provided, and since a nuclear battery is much more compact than a reactor, both the weight and the dimensions of the car remained within reasonable limits. The Lubier brothers were already rubbing their hands in anticipation of assembling a batch of 100 cars for taxis, as well as participating in the 24 hours of Le Mans race in '59. But their plans were not meant to come true. The French government did not approve the use of nuclear fuel, and further work on the concept naturally stalled. The unusual prototype Studebaker-Packard Astral was built in 1957 and was first presented at the South Bend Art Center on January 12, 1958, and then at the Geneva Motor Show in March of the same year. The Astral was developed by Edvardo Herman, the company's chief of design. First and foremost, the project was conceived to give the team experience working with fiberglass. And along the way, they added every possible bit of futurism to the design: a single wheel with gyroscope balancing, a nuclear power unit, which, by the way, wasn't technically developed at all, and almost even the ability to fly. Here's an image as proof. If the previous two concepts at least bothered with calculations for nuclear installations, then Packard simply announced, "Here, it will be nuclear." The concept car was driven around the dealership center before being put into storage. 30 years later, it was restored and put on display at the Studebaker Museum. Officially presented at the Geneva Motor Show in 1959, the Simca Folger show car was supposed to predict the cars of the year 2000. At that time, Simca was one of the leading automobile companies in France, producing up to 100,000 vehicles a year. As widely acknowledged, large companies not only manufacture practical vehicles, but also strive to make a statement about themselves through their products. Races, exhibitions, records, etc. At Simca, they decided to present their vision of the car of the year 2000 at the auto show. In the Simca Folger, they wanted to use voice control, radar, the option to drive on two wheels with gyroscopic stabilization, and a nuclear reactor as a power source. At Simca, just like at Studebaker-Packard, they didn't really bother thinking through the power unit, based on the principle, once someone makes a portable reactor, we'll just install it in the car. For now, enjoy the exhibition. Ford didn't give up on their ideas, and in 1962, another concept car followed, which was being prepared for the International Exhibition in Seattle. The concept was built full-sized. At first glance, it was another futuristic project from the 60s, distinguished only by 4 steerable wheels in the front and a very low semi-reclining seating position. This prototype was created by Alex Tremails, a talented car designer who had been working at Ford since the 50s. One of his works was the gyrocars Ford Gyron in 1961. The Ford Seattlite 21 concept was developed as one of the visions of the car of the future, the car of the year 2000. By 1962, Ford had already realized that a miniature nuclear reactor that could be integrated into a car chassis might not appear as soon as the optimists of the peaceful atom had thought. Therefore, when presenting the concept, the company literally stated the following: "Ladies and gentlemen, as soon as a nuclear reactor is ready, great, we'll install it in the car. For now, you can just put a V8 engine in there." The developers believed that for city conditions in Seattle, a 60 horsepower engine would be enough for the 21. If you want to travel or crave some excitement, you can swap it out for a more powerful setup, something around 400 horsepower. To truly amaze the visitors at the fair and show them a real car of the future, the creators of the Seattlite 21 packed the concept car with a ton of ideas that seemed like science fiction at the time. Here you have a navigation system, a rain sensor, parking sensors, automatic window tinting, and a large color monitor. And eventually, all these technologies became reality. There is no reliable information about the fate of Symétric 21. Perhaps the concept car is hidden somewhere deep in Ford's warehouses, or maybe it was lost a long time ago. After reviewing a number of foreign concept cars, a natural question arises. What was the situation with similar developments in the Soviet Union? In the late 20th century, the Soviet Union was a leader in nuclear technology alongside the United States. With the commissioning in 1954 of the first nuclear power plant, let me remind you this was the Obninsk nuclear power plant, the question arose about creating a mobile nuclear power station to supply electricity to facilities located in remote and hard-to-reach areas of the country. And yes, the TES-3 is not a civilian vehicle at all, but it is a very interesting design that is definitely worth paying attention to. Sketches for the mobile nuclear power plant emerged in 1957. By 1961, just 4 years later, the TES-3 was produced. The TES-3 was developed at the Obninsk Institute of Physics and Power Engineering's Laboratory 5. The chassis of Object 27 was developed at the AKB Kirov plant by lengthening the chassis of the T-10 tank. The complex could be transported on platforms, by rail, or by water transport to the final destination, and then move under its own power to the designated point. The complex consisted of 4 self-propelled components in total. The first housed the reactor, whose active zone was a cylinder with a diameter of 660 millimeters and a height of 600, inside which there were 74 heat-emitting assemblies. It was a 2-circuit water-water reactor with a thermal power of 8.8 megawatts. The reactor itself, or more precisely its active zone, was located in a massive lead vessel, which in turn was placed in a tank. In the working position, the tank was filled with water, and during transportation, the water was drained from the tank. The second transporter contained the steam generator, circulation pumps, and other equipment involved in the operation of the reactor installation. Electricity was generated on the third machine of the complex. It was there that the steam turbine unit was located, capable of delivering 1.5 megawatts of electric power. And the fourth installation housed the control and monitoring panel, as well as the auxiliary emergency diesel generator unit and batteries. In working condition, all 4 machines were connected in a specific sequence by pipelines, control cables, and power cables. Moreover, the reactor and steam generator sections were installed at a distance from the electrical and control sections. In addition, for extra protection, earth embankments were piled up on the sides of these sections, and additional concrete shielding was constructed. The tests of TES-3 were conducted at the Physical Energy Institute in Obninsk, beginning in 1960. In 1961, the station entered operational mode during testing and ran until 1965, when fuel assemblies required replacement. The total weight of all the additional equipment on the 4 self-propelled vehicles was 210 tons. The TES-3 operation confirmed its functionality, clarified nuclear power plant and thermal power center principles for remote areas, and provided first-time experience in self-regulated nuclear power plant operation. At the beginning of '67, the military department abandoned the concept of using such power plants. There was also no interest from civilian agencies, and work on TES-3 was suspended. Subsequently, the option of using the reactor unit to produce a large volume of hot water was considered, which was needed at some oil fields to bring oil closer to the surface. But this idea was never implemented, and in '69, the unique self-propelled nuclear power plant was mothballed forever. In the '80s, the further development of the idea of transportable large-block nuclear power plants of small capacity was realized in the form of TES-7 and TES-8. In '73, work on this topic was continued in the Belarusian Soviet Socialist Republic, when a special design bureau was created as part of the Institute of Nuclear Energy. As a result of many years of work, in '85, the mobile nuclear power plant Pamir 630D was created and launched. For testing the installation, 2 sets of the mobile nuclear power plant were manufactured. The first of them was intended for field trials under real conditions, while the second set was used for energy tests on test stands. The first Pamir reactor was electrically started on November 24, 1985. The tests continued until September 1986. The experimental model operated for a total of about 3,500 hours under various load conditions. The unit was brought to its design capacity twice. The thermal power of the reactor unit was 5 megawatts, and the electric power was 630 kilowatts. The reactor and turbo generator units were placed on 2 special semi-trailers. As the main tractor for the installation, a MAZ 7960 automobile was used. The station was serviced by about 28 people in total. The installation was designed to be transported by rail, sea, and air transport. The catastrophe at the Chernobyl nuclear power plant in 1986 put an end to further development of Pamir and TES 7 and 8. Work on the Pamir 630D project was stopped. However, the technical documentation and experience remained. And in news articles of 2020 and 21, there was information that work was underway in Russia on the construction and testing of a similar installation. However, let's go back along the timeline to the early 60s. Paying attention to American concepts of the atomic car, Nikita Khrushchev gave the task to domestic scientists and engineers to develop a civilian passenger atomic car. In the early 1960s, engineers from a closed car design bureau, led by physicist Alexander Kamenev, started the project. He personally designed the main element of the Volga atom, the nuclear unit. The base for the Volga atom was the production model GAZ-21 Volga. The most interesting thing about this car is its power unit. The A2 engine was a fairly traditional 4-cylinder unit, except its fuel was uranium-235. On the ends of the cylinder pistons, there were washers made of enriched uranium. At the end of the cylinder, there was also a washer made of graphite, which acted as a neutron moderator. Helium, pumped into the cylinders, served as the working fluid. During the compression stroke, the uranium masses moved closer, increasing the neutron multiplication factor. The helium heated up due to the heat release and expanded, pushing the piston. This was the power stroke. It was possible to control the revolutions and stop the engine using absorber rods, which were located in place of the valves and were extended by a camshaft with variable cam phases. As the nuclear fuel was consumed, the phases were shifted to compensate for its burnup. The power unit weighed about half a ton. It was precisely so that the chassis could withstand this weight that 2 pairs of front wheels were used, all of which were steerable and received torque. The engine produced 320 horsepower and about 800 newton meters of torque. In 1965, the Soviet car was sent to the test range. The tests conducted showed that the design was fully functional. At the same time, the range on nuclear fuel was supposed to be about 60,000 kilometers, after which the power unit would be replaced. However, it turned out to be impractical to continue developing the project. 2 prototypes were built, which were later dismantled and disposed of. Now let's move to the present day. The 21st century has given the world at least a couple of prototypes of nuclear-powered cars. The first among them is the Cadillac World Thorium Fuel. This concept car was developed by Lauren Kulisis in 2009. The main idea behind the development of the concept was to present the design of a car capable of operating daily for 100 years without repairs or refueling. To achieve this goal, the author of the concept suggests using wear-resistant materials, duplicating key systems to increase durability, and employing a nuclear power unit running on thorium. By the way, nuclear scientists in the 21st century are not looking at thorium for no reason. For For example, the reserves of this radioactive element on Earth are 3 to 4 times greater than those of uranium. For this Cadillac, the company Laser Power Systems was developing a thorium-based power unit and planned to put this unit into mass production. The company managed to achieve a unit weight of only 250 kilograms, which is comparable to the weight of a modern V8 engine. The most remarkable thing about the design of the Cadillac WTF is its wheels. Each of the 4 wheels consists of 6 separate segments. Each segment has its own electric motor. Thus, Colesis intended to ensure the longevity of his design for 100 years, remember? And here is a brand new car concept called SpaceX Fusion Concept, presented in 2022. By the way, it has nothing to do with Elon Musk. This concept was developed by designer Kellen Gustin. He is considering the possibility of using an HB11 reactor in this car. The operating principle of this reactor is not based on the decay of radioactive elements, as in all the previous designs considered, but on the synthesis of hydrogen atoms and boron-11, atoms under the influence of laser radiation. The HB11 reactor promises to be much safer than nuclear reactors. The compact thermonuclear reactor is planned to be installed in the rear part of the futuristic car. The idea is quite interesting, both in terms of a means of transportation and in terms of creating a compact, environmentally friendly, and safe reactor. If you're interested, just Google the HB11 reactor. In 2022, Rolls-Royce announced plans to create a mini reactor. The dream of creating a nuclear-powered car has been in the air for 7 decades already. Consequently, we have various concepts, including mobile nuclear power plants and the dubious creation of the Volga atom. These ideas never became mainstream due to a lack of widespread appeal, not because of a conspiracy between Freemasons and security services. There is a much simpler and far more logical explanation for this. First of all, a nuclear car is more complex and expensive to manufacture. Using a nuclear energy source requires higher quality and more costly materials. The qualifications of workers in the automotive industry and the service personnel at maintenance stations who will be dealing with the power unit must be significantly higher. Secondly, the main problem with a car that has a nuclear reactor is creating a safe radiation environment directly near the reactor. LEED does a decent job, but it makes the construction damn heavy. Another pressing issue is where to put the heat from the reactor. About 3/4 of all the reactor's energy will turn into heat, which will be around and inside the car. Nuclear power plants, submarines, and ships don't have this problem because they have a large amount of water nearby. Lastly, and most importantly, I believe each of you has encountered road traffic accident statistics for your country or hometown at least once. You know very well how many cars crash into poles, guardrails, and each other every year. And now imagine that these are atomic cars. A severe traffic accident with these vehicles has a chance of causing environmental contamination. And if such a car falls into the hands of a terrorist, it's basically a dirty bomb on wheels. So it's a good thing that all these ideas about a mass-produced civilian atomic car never went beyond concepts or a few prototypes. As for special atomic equipment, which will be operated by trained personnel, like the TES-3 for example, I'm much more loyal to such designs, although even trained staff sometimes encounter emergency situations. As of the year 2023, the possibility of implementing thermonuclear fusion and thorium reactors remains interesting. It's important to note that these technologies still face numerous challenges and unresolved issues. What will happen in this industry next, time will tell. And so, my friends, this story concludes. Thank you very much for taking the time to watch this video. If you liked it, don't hesitate to give it a like, recommend the story to good friends, and subscribe if you haven't already. Special thanks to everyone who supports the channel financially using the details provided in the description. This was the Krasmodo channel. See you next time.